Here we go. Let's see, where do we start? Today we're going to have a review on Chapter 18 for Exam 9. That'll be on Thursday the 5th. But we have to meet class in room 138, which is just down the hall in the laboratory. This administration needs to use this room for something else. I'll post a note on the door in case you forget. And then we'll have that exam on the 5th, and then our final is on Tuesday the 10th at the same time, same place. And it will be comprehensive. Okay, any other? I think that's it. We can get to the review now. Rebecca should be here. She's not here yet. Hope she's not having trouble zooming in. Check for messages. That's not what I'm looking for. Okay, that's fine. Well, we'll get started anyway. Okay. Electrochemistry, also known as redox reactions. Okay, does anybody have any special problems we want to deal with first, or you want me to just jump in and start talking? I'll take that as an indication for me to proceed. Okay, so let's do a short review on what a redox reaction is. Transfer of electrons is required. Anytime you transfer electrons, you have a redox reaction. And how do you know which is which? Well, remember that oxidation is loss of electrons, and reduction is gain. Okay? So, probably the most important rule to remember is you can't have one without the other. Anytime you have an oxidation in a reaction, you have to have a reduction. They never occur separately. So let's take this number one as our starting point. Good place to begin. And we have this reaction. And it yields this compound. Okay? Just so happens that that's balanced. 1 barium, 2 chlorines. Question is, which of the following is true? Well, let's take A. What does A say? The barium atom is losing electrons, therefore it is oxidized. In order to know whether electrons are being transferred and where they're being transferred, you need the oxidation state of each element. Any element in its standard state is 0. So each one of the barium atoms is 0. Each one of the chlorine atoms in that pair is 0. In the compound, halogens are going to be 1 minus. And barium, since it's in the second group, is going to be a 2 plus. So Two of these 2 minuses balance that 1, 2 plus. Okay, so that's good. Now we can answer the question. Barium atom is losing barium loss of electrons, which says oxidized. So is that true? Barium's lost that, that's true. Okay. So, test-taking technique. Since we found the true one and there are no other options in there, that's the answer. The rest of B, C through D, B, C, D are all false. So what else is happening? Let's just take this as an opportunity to hash out various terminology for oxidation reduction reactions. What else is happening? Well, chlorine is gaining electrons. And one of the ways that I like to keep track is to say this. Okay, so barium loss, 2 electrons per barium. Okay, chlorine is what? Well, it gains 1 electron per chlorine times 2 chlorines equals 2 electrons. So we transfer 2 electrons from barium to the chlorines, and each chlorine got 1 electron. So that means chlorine is reduced and barium is oxidized. Okay? They always occur in pairs. So if you have something being reduced, you need a reducing agent, something that's responsible for reducing chlorine, and that's barium. So barium is the reducing agent. And that makes chlorine the oxidizing agent. Okay? That's not part of the question, but I couldn't help myself. Let's see, I think, yeah, everybody's muted, so if you want to say something, be sure to unmute yourself. Okay, so we got the basics out of the way. Let's see, 2, 3, 4. So calculating oxidation states is essential. So we need to figure out, for 4, what's the oxidation state of sulfur in this compound, right? So we're looking for the oxidation state of sulfur. So in order to do that, we have to have some assumed oxidation states for the other elements. And oxygen is always 2 minus, and potassium is always 1 plus. It's an alkali metal, and oxygen, being a chalcogen, is taken as 2 minus, but that leaves sulfur free to be calculated. So those are a couple of rules. Another rule is a compound is neutral, right? So all the oxidation states have to add up to 0. So with 3 oxygens, we have a 6 minus here. With 2 potassiums, we have a 2 plus here. And then these 2 together are 4 minus. That means this one has to be a 4 plus to balance these 2. Okay? Now, what do you do if you have, well, let's see. if we have an example like that. I want to find a complicated one. So we have to make a decision which one to assume is a certain value to calculate the others. Well, let's try 21. Actually, 21 and 22. We'll start with 21. So 21 is this compound. Okay? And the question is, what's the oxidation state for carbon? Well, actually, 22, it would be better to take 22 first, because 22 asks us a question that we need to know to answer 21. Right? 22 says, what's the oxidation state of iron? So let's do 22 first. What would be the oxidation state of iron? Well, in a compound like this, it would be the charge. Right? What charge does iron have? You know, carbonate is a polyatomic ion with a 2- charge for the whole thing. So 3 times 2 minus is what? 6 minus. That means these two irons have to balance it with 6 plus. That means iron is 3 plus. Okay? Now that we know that iron is 3 plus, and we know that oxygen is 2 minus, we can approach this 2 different ways. You can take it as a neutral compound and say, you've got 3 times 3 is 9 oxygens, is 18 minus charges. And we've got 6 plus here, right? So that's 12 minus. And we have 3 carbons, right? So 3 carbons have to balance that with a plus. Right? So 3 times 4 is 12 plus to balance that one. Or we know the charge on this polyatomic ion, right? And we're looking for carbon. So if this is 2 minus, and we have, for the whole thing, 2 minus, and each oxygen is 2 minus, so we have 6 minus for the oxygen, and we have to hold 2 minuses out for the charge. That means we only have to balance 4 minus with carbon. So carbon is 4 plus to balance that. So either way works. We know now that carbon is a 4 plus oxidation state. By the way, when is oxygen not 2 minus? One situation that I know of. When it's part of a peroxide. Oxygen and a peroxide, both of these together are 2 minus. So each one is 1 minus. Right, so if you ever run across a peroxide, then you count each oxygen as 1 minus. If you need to determine the oxidation states on any of the other components. R1 and R2 could be anything. They could be, or usually they're organic. Okay, let's see if we can find something else that I haven't talked about yet. How about 28? When metals react, what happens to the metal ion? Oh, the metal atom. If you're going to react a metal with a nonmetal, which way do the electrons usually flow? They usually go from the metal to the nonmetal. Which means they lose electrons. So they're oxidized. Typically, a metal reacting with a nonmetal will always be oxidized, and the nonmetal will be reduced. Okay, let's see what else we can find. Oh, this is a good one, 30. So for each one of these compounds, we're looking for the oxidation state of nitrogen. So let's write all our compounds up here. C, D, E. And this one. Okay. Now, if you look at your at the periodic table in the back of the useful information, back here somewhere. Here it is. You'll notice that if you look at nitrogen down the right-hand side of the little cube, you'll see that thing is chock full of oxidation states. Nitrogen is one of those atoms that has an apparently unlimited number of oxidation states. Not unlimited, they're just lots of them. So each one of these could be a different oxidation state. That's perfectly valid. So we're going to assume values for everything except nitrogen. That way we can calculate nitrogen. And remember, oxidation states are not necessarily reality. Oxidation state calculation is a bookkeeping technique. Now, very often, they are real or close to real oxidation states. Not necessarily charges, though. But they're just a way for us to keep track of our electrons, and we continue to use them because they work. Okay, so what's the oxidation state of nitrogen here? Well, hydrogen is +1. Oxygen is a 2-, which makes 6-, and then a +1 equals 5-. Okay? So that means nitrogen has to balance this 5- with a 5+. So let me go back to 30. 30. Here we go. That's not it. We're looking for +4. So for this one, oxygen is 2- again. That gives us a 4-. So this nitrogen has to be a 4+. There's your answer. That nitrogen is 4+. Let's go ahead and do the others while we're here. This one is a 2- by itself. So that nitrogen pair has to balance with a 2+, which means each one of them is 1+. Okay? You can do this one 2 different ways. Ammonium is a polyatomic ion with a +1 charge. So you could calculate this, and it doesn't matter what that one is. But if you do it as a compound, they just have to add up to 0. Right? So chlorine's -1, oxygen is +1, which means a +4, and a -1 yields 3. So that means this nitrogen has to be 3-. And for this one, Sodium is +1 because it's a alkali metal. Oxygen is 2 minus, so we have a 4 minus here and a +1 here, and that gives us a 3 minus. That has to be balanced by a 3 plus. So now we know all the oxidation states of each of these nitrogens, and they're all different. This nitrogen's +1, +3, +4, +5, and you even have a -3 for that nitrogen. But the answer to the question, as given, is B for number 30. Okay. Let's see what else we can come up with here. Let's get on to some more advanced stuff. How about number 42? Identifying which reactions are oxidation reduction and which ones are not, because not all reactions are oxidation reduction. So we've got these 4 reactions. Okay, PCl3 plus Cl2 yields BCl5. Copper. And this one, and the last one. Let's see if I wrote those right. Okay. Yep. Okay. So the question is, which of these are oxidation reduction reactions? Well, we can use that little trick I mentioned. If you have an element on one side of the arrow and it ends up in a compound on the other side, you know that's oxidation reduction. So we can tag this one. There's an element. It's in a compound over here. So that one's oxidation reduction. Here's an element in a compound, or an element out of a compound, works both ways. That one also is oxidation reduction. The other two, we don't have that indicator. So in order to know if this is oxidation reduction, we've got to do the oxidation states on each of the elements and see if any of them change. Okay, the easiest one to do is lithium. Because lithium in a compound is an alkali metal, so it's always +1. Oxygen, hydrogen is +1, oxygen is 2 minus, so that balances. Here's lithium, here's oxygen, 2 minus, so that's 6 minus total, and then lithium is a +2 total, right? So that means we have a 4 minus here. It has to be balanced with a 4 plus there. So carbon is 4 plus there. So what's carbon over here? Well, each oxygen is 2 minus, so that's a 4 minus, that's a 4 plus. Carbon didn't change. Lithium didn't change, oxygen didn't change. So that one is not an oxidation reduction reaction. Okay? Do the same thing with this one. Halogen, this is 1 minus plus 1. This is a minus 1 charge with a plus 1 here and a minus 2 there. But the minus charge for the hydroxyl means that you have 2 minuses there. So this is 2 plus for iron. This is a minus 1, so it's a 2 minus total. So this is 2 plus. Iron didn't change either. Sodium didn't change. Oxygen didn't change. Hydrogen didn't change. That's not oxidation reduction either. So the only two out of this group that are oxidation reduction are Roman numeral 1 and 2. Okay? Let's see. Let's do 43. A little reasoning problem here. Which of the following is true or are true about redox reactions? Okay. A, cannot occur independently. Is that true? That's true. Can't have one without the other. That one's true. How about B? Redox reactions accompany all reactions. Are all reactions redox? No. We just worked a problem that showed that some of them are not. So that one's false. Redox reactions describe the loss and gain of electrons. Loss and gain of electrons, respectively. So what does that mean? Respectively. Respectively means that when we say oxidation reduction, as in the question of the problem, oxidation reduction respectively means this one refers to that and this one refers to that. That's true. And D, they result in a change in oxidation state of the species involved. Change oxidation states. That is true. So out of these four choices, E is the answer because it says A, C, and D are true. All right. That's 43. We're doing good on time. Let's see. Let's do 49. For 49, we actually have to balance an equation using the half reaction method. Okay, you remember the half reaction method? This is where we're starting. Okay. Iodine chromium 3 plus, and element iodide. So these are aqueous. That's a solid. This is aqueous. This is aqueous. One thing you may have noticed or may not have noticed is that redox reactions, when they're given like this, just recognize that this is a negative ion and that's a negative ion. The logical question you should be asking yourself is, where are the cations? Right? Because you can't have an unbalanced charge. Well, we write them this way because it doesn't matter what the cation is. The cation for that one and the cation for that one are irrelevant. They're spectators, right? And they just get in the way. Balancing the equation, all you need are the active players. And that's what these are. That's an active player, active, active, active. So it doesn't matter what their counter ions are. Now, first thing you have to do when you're balancing one of these equations is decide which reaction is the oxidation and which one's the reduction. And to do that, you've got to determine oxidation states. Okay. So the easy one is the element. That one's 0. That one is -1. Now we need to find out what happened to chromium, right? Well, you can assume that if this one was -1 and it went to 0, it had to lose an electron, right? Had to lose an electron. So that means the iodide ion was oxidized. That means this one should be reduced. Let's just prove it then. 7 times 2 minus is 14 minus, but we have to hold out 2 minuses for that charge, so we only have to balance 12 minuses. And 12 minuses against chromium, well, plus each one of these chromiums is 6 plus. Okay, so we got that chromium, and this chromium is 3 plus. So now we can write the half reactions. So the oxidation reaction is this one, which is, let me make some more room here, is the iodide ion yielding elemental iodide. And then the reduction reaction is the dichromate, okay, yielding the chromium. Okay, so let's keep track of everything. That's -1, that's okay. Now, what's the next step? Balance everything except oxygen and hydrogen. So we have 1 here and 2 there. We need 2 here. Oh, by the way, it's also a good idea, once you write these as oxidation reduction, to stick an electron in there, just as a placeholder. So oxidation means this one lost an electron, which means it's on the product side. Okay, and this one being reduced, we added an electron, 1 or more electrons here. Okay, so that one's balanced for iodine. Chromium, we need 2 here. Okay. Now we balance what? Oxygen comes next. And how do you balance oxygen? Well, we don't have any oxygens here, so we can leave that one alone. But we do have oxygens here. On this side, we have 7 oxygens, and we need 7 oxygens on this side. And oxygens always show up as water. Okay, but now what have we done? We've added 14 hydrogens on that side. We need 14 hydrogens on this side as protons. Okay, now we balance electrons. if we went from a -1 to a 0, that's 1 electron. Well, we've got 2 of them. So we actually end up with 2 electrons on that side. On this side, we went from a 6+ to a 3+. So that's 3 electrons. Add 3 electrons to that 6+, and you get a 3+. But we have 2 of these also, right? So that means we don't add 3 electrons, we add 6 electrons. Okay? Now, next thing you want to do is balance the electrons between the 2 equations so that now that you add them together. Because you can't transfer 2 electrons for one and 6 electrons for the other. They have to balance. So if we're going to add 6 electrons here, we have to end up with 6 electrons there. So that means times 3. All right, so 3 times this, 6, and 3 times this is 3, 3 times that is 6. So now we have 6 electrons on both sides, and they will cancel when we add them together. Okay, so we can bring things down. We've used that up, so it's already there. Okay, so we've got 1 chromate, dichromate. We've got 6 iodides. Electrons canceled. We have 14 protons. So that's everybody accounted for. 1, 2, 3. 1, 2, 3. And on this side, we have 2 bromine 3+ and 3 iodines and 7 waters. Now, then you look for anything that occurs on both sides that you can balance out, cancel out. Right? This is only on one side. Oop, I'll let that charge. That's only on this side, that side, that side. So that's everything. It's balanced the way it is now. So let's go back to the question. 49 said, what's the coefficient for the iodide ion? Here's the iodide ion, and the coefficient is 6. Okay? After you balance the equation like that, you could ask any question here. You could say, all right, what's the coefficient for water? Right, be 7. What's the coefficient for the iodine molecule? 3. Right? Or what's the total of all of them? Right? So what would be the total? Well, 7 plus 3 is 10, plus 2 is 12, and 12 and 24, 12 and 14 is 26, and 6 is 32, and 1 is 33. Don't forget that 1, if that question is, what's the total of the coefficients? Let's see, while we're here, this right here says that the solution is acidic. This takes place in an acidic solution. But what if the problem says balance this for a basic solution? What do you do then? Well, you come to this point with acidic, and then you convert it to a basic. And how do you make it basic? You add hydroxyls. You add enough hydroxyls to neutralize those acids. Right? So 14 hydroxyls will balance those, and that makes 14 waters. Right? Hydrogen ions, hydroxyl ions together make water. So we have 14 waters here Then we have to add 14 hydroxyls over here. Okay? Then you look for things that you can cancel out, balance out. Well, now we have 7 waters over here, 14 over there. These waters go out and leave us with 7 on this side. So in basic solution, this is dichromate, 6 iodides, 7 waters, 2 chromium 3s, 3 iodine molecules, and 14 hydroxyls. That's how you balance your basic. If the question is, balance this equation in basic solution, you do the acidic first, then you convert it to basic. I don't know, there should be one like that in here somewhere. But I saw this is the best opportunity. We already balance it in acidic, so we just make it basic. Okay. Let's see. Let's do 52 next. A word problem that you have to convert into reactions. Okay. All right, 52 says, for the reaction of sodium bromide, okay, you gotta know how to write the compound, with chlorine gas, diatomic. It doesn't say solution, so this is probably a solid. Okay. To form sodium chloride. And what else? Bromine. That's going to be a liquid, right? In its standard state, bromine is a liquid, but it's diatomic, right? Because all of these are diatomic, plus hydrogen. Now that we've written that correctly, the question is, what are the half reactions? If we write this in a half reaction setting, oxidation over here and reduction over here, based on the answers, oxidation on the left, reduction on the right. What are the oxidation states? Well, chlorine is 0, bromine is 0. They're elemental in their standard states. Bromine is a halogen in this compound, which is -1, that's +1. This is +1, that's -1. All right? So, it looks to me like the answers are expecting a balanced equation first also. Fortunately, we can balance this equation without doing the half reaction method. Right? All we have to do is say, we've got 2 chlorines here, we need 2 chlorines there. We got 2 bromines there, we need 2 bromines here, and that balances the sodiums also. So that balances the equation. So now all you have to do is decide which one's the oxidation. Which one gets oxidized? Oxidation is loss. Which one loses electrons? Bromine loses electrons. It goes from a -1 to a 0. So we're actually going from this one to this one. Oops, that's not right. Is it? Because nothing's happening to sodium. Plus 2 electrons, right? 2 negatives to 2 zeros is 2 electrons. So that's the oxidation side. The reduction side is the chlorine. Actually, since it's reduction, we have to add electrons. And then we end up with 2 chlorides, right? 2 chlorides from chlorine. And this one has to have the same number of electrons on this side as that one. And let's see if that works. If this is 0 for both of them, add 1 electron each, you get a negative for each one. So that's the answer, and it turns out that that's B. Okay? Let's see. We have several other equations that require half reaction balancing. How about 59? '59 will test whether you actually read the textbook or paid attention in class. So 59 says, what type of battery is in the automobile? Right, you have dry cell. So what's a dry cell? It's what we normally think of as the D's, C's, AA's, AAA's that go in various devices. That's a dry cell. But there are specific types of dry cells. Alkaline dry cell is one type. So you might surmise that there are also acidic dry cells. Right? If there's one alkaline, then there's also an acidic type. But this is typically what you put in your flashlight. Let's see, where was I? Here we go. Lead storage. That's the one that's in an automobile, right here. The lead storage batteries in your automobile. Then you have other types. The mercury cell, which used to be used in hearing aids and calculators, but they don't use them anymore for obvious reasons. And then nickel cadmium is a type of battery. I think I described it in class. It was the battery that ran my trimmer. They have a notorious problem with nickel cadmium batteries is they have bad memory. In other words, if you only partially discharge it and then recharge, then it thinks that it's the place that it left last was 0. So it'll go down to the point where it was last at when you started recharging it. It thinks that's 0. So what you have to do is you take it, turn it on, and drain the battery completely dead. And that resets at 0 point. Then when you charge it up, you've got the full capacity available. Unfortunately, they have a limited life. And so I had to retire my nickel cadmium trimmer, and I went out and bought another one. Now they're putting lithium ion batteries in them. Just like cell phones, laptops, lithium ion batteries are everywhere. Okay, so that's the one that's not up here. Lithium ion batteries. And you'll find those in cell phones, laptops, you know, what's the tablets. Those are the ones I can think of offhand. Lithium ion has a higher energy density. That is, for the same mass of battery, you can store more energy in a lithium ion than you can in any one of these. Right? That's why they're popular. And one of the reasons for that is lithium is the third lightest element in the chart. So you can pack more of them together. And all you need is one lithium to transfer one electron. So the more of them you can get in there, the more energy that you can store in that battery. Okay, that was 59. See how we're doing on time. Okay, we're good. Let's see, something. Oh, okay, 60. What's the electrolyte in a lead storage battery? You remember that? You have one plate is made out of lead. The other plate is made out of lead oxide. And in between them is sulfuric acid. This is the electrolyte. In a lead storage battery. Okay? And in the reaction, this one combines with that one to make that. And this one combines with that one to also make that. Right? So, and in each case, the oxidation state of lead changes. In this one, it's 2+. Let's see. No, wait a minute. That's not right. It's 1+. Now it's 2+ here, and here it's 2+, but here it's 0. So the oxidation states of lead for this one loses an electron, it's oxidized, and this one is reduced. No, that's not right. This one's oxidized. That's not right. Why is that not right? I think it's that. No, that's not right either. That's sulfate. That's 2+, 2+. If this one's going from 0 to that one, it's oxidized. So this one has to be reduced. So if it's going to 2+, this one has to be +4. There you go. So this one's being reduced, this one's being oxidized. And the participant in the reaction for both of them is sulfuric acid. Okay, let's see what else we can come up with. What's electrolysis? Electrolysis is a process which actually drives a reaction in reverse. For a battery, you're extracting energy from the battery because the reactions that are being used in the battery are spontaneous. So they produce an electric current for you, exterior to the battery, so that you can use that energy. Well, if we want to go backwards, like we have a battery in our car, there's an alternator also that runs off the engine, and it supplies electricity to run those reactions in reverse. So it remakes lead and lead oxide from lead sulfate. Right? So we add electricity to it, and we drive the reaction backwards. That's electrolysis. So for 64, which of the following is true? Well, electrolysis is a process where electrical energy is used to produce a chemical change. That's true. A is true. How about B? Electrolysis involves forcing a current through a cell to produce a change that would otherwise not occur. That's saying that the reaction that we want is not spontaneous. We have to provide energy to run it backwards. That's true. C, the electrolysis of water produces hydrogen gas and oxygen gas. That's also true. Normally, what you have is hydrogen gas and oxygen gas make water. Right? That's what happens in the space shuttle engine. Liquid oxygen, liquid hydrogen are gasified in the engine. They're vaporized, and then they react to produce water and massive amounts of energy. That's how the space shuttle gets into space. Well, along with its solid rocket boosters. But one way to make each one of these is to drive the reaction in reverse. Provide electrons at a high enough voltage, and you split the water molecule into its atomic constituents. Right? So you're oxidizing oxygen, removing electrons to make this, and you're reducing hydrogen, adding electrons to make that. That's also electrolysis. Let's see. D, electrolysis is used to recharge a lead storage battery. Well, that's true. I just told you that one. So that means E is the answer, because E says all of them are true. Okay? You can do that electrolysis of water yourself. All you have to do is take some water from your tap. It may or may not need any acid in it, but if you need some acid to conduct electricity, just put a couple of drops of lemon juice in it. And then you take a 9-volt battery, drop it in that glass of water, and you'll notice pretty soon on each one of the electrodes, gases are forming. One electrode forms the oxygen gas, the other electrode forms the hydrogen gas. So this one, we didn't talk about this one in class, but it is in your, it's in the slides, and it's also in your book. The Hall process for making aluminum. The Hall process. The Hall process is a process of electrolysis. Right? It basically takes aluminum ore and melts it. Now, why would we have to melt? Normally, aluminum oxide is a solid, right? So what happens to a crystalline solid when you try to drive electricity through it? It doesn't happen, right? These ions are locked in place. They're locked in the crystal structure. So the only way to get them to move and conduct electricity is to melt them. So these are melted along with some other things, right, that make the process more efficient. But this is the primary part of the reaction. And then when you add electricity, electrons to this, actually you add electrons here, and you change this from 3+ to 0. So for each one of those aluminums, you're adding 3 electrons, and if you have 2 of them, that means 6. Right? So that's, in a nutshell, the Hall process. And actually, the invention by this guy right here, Hall, made aluminum affordable. So we can have aluminum foil, we can have, you can make silverware, not silverware, flatware out of aluminum if you wanted to. In fact, royalty in Europe, when aluminum was first discovered, royalty would serve their big banquets using aluminum flatware because it was more expensive to make aluminum than it was to mine and extract and purify gold. Aluminum was more expensive than gold then because of the way they had to produce it. Now, with this process, it made aluminum dirt cheap. All you need is a cheap source of electricity. And you can get that, at least in this country, you got that 2 places. Where coal was very plentiful to produce electricity, like in Pennsylvania, Tennessee, Appalachian region, or any other place where coal was mined, actually, or where hydroelectric power is available, which is also dirt cheap, because you need lots of electricity to do this process. So a lot of fertilizer plants and aluminum processing plants like Alcoa got its start in Pennsylvania, sprung up in these coal-producing regions and along rivers that have been dammed and producing hydroelectric power, like the Tennessee Valley Authority. Of course, they didn't set up those factories out there in Nevada, right? Because all the power being produced by the Hoover Dam was sucked up by the gamblers in Las Vegas. So manufacturers had to go someplace else. Okay, so that was 65. By the way, 65, answer 65 is C. Electrolysis of molten aluminum and sodium aluminum fluoride. Sodium aluminum fluoride is added, and it has to be molten. You don't want aqueous solutions of this stuff. Why? Because when you start driving electricity through an aqueous solution, what do you get? You get hydrogen and oxygen, right? You don't get aluminum because it just electrolyzes the water. So it has to be molten. Sodium aluminum fluoride is added because that lowers the melting point of aluminum oxide. So the whole thing melts at a much lower temperature. You don't have to add as much heat to get them into that liquid state. So that's why C is the answer for 65. Let's see, there's some other redox reactions. You can do those on your own. More. There's lots of practice balancing redox reactions. Let's see. There's some practice doing basic solution reactions. Okay, I don't see anything new other than that. Okay, so we got a few more minutes if you have questions that that I didn't cover, and you want to talk about something that's of concern. Okay. No, I don't hear any objections. And Rebecca never showed up either. I wonder if she had trouble zooming in. Yeah, at least we'll have the video. And remember, next Thursday, go to room 138. I'll put a note on the door in case you forget. And the only thing we have to do is just take that exam and then follow up the next week, final exam. Okay, I guess we're done then. If everybody's happy, I'm happy. We'll see you on Thursday.